we've already discussed how prevalent binary stars are. Close to half of the stars in our part of the galaxy turn out to be binaries. So the question is, does that have any effect on stellar evolution? And won't expect that it would. And so the question as to what happens really depends on how close the binaries are. If we have two stars that are very far apart and one of them swells up and does all kind of things, the other star's probably going to be far enough away it doesn't really matter. But if the stars are close enough together that one star starts interacting with the other, then that's going to drastically change the evolution of the star that's. So the key comes from a mathematician by the name of Roche. Carl Roche realized that you can calculate that there's regions of space where one star's gravity dominates the other. We call those Roche Lobes. So you would have, for example, a star here on the left, and the region of space where that star's gravity dominates is that star's Roche Lobe. And so, and then the other star over here, the region of space where that star's gravity dominates is going to be that star's Roche lobe. And so each star's Roche lobe is going to be determining what happens. So when a star dies, it's going to swell up and fill its Roche lobe. Now, right in between the two is where you have the gravity of both stars pulling evenly. That's what we call the inner Lagrange point. And so that Lagrange point, so if one star were to fill its Roche lobe, and really what would happen is it'd be the bigger star that fills its Roche lobe, because it's going to die first. And if it fills its Roche lobe, stuff that's right in the middle can actually spiral into the other star. Well, what's the outer parts of this star? It's mostly hydrogen. So they'll be dumping hydrogen onto the smaller star. So that's going to lessen the mass of the big star and increase the mass of the small star. Detached binary, this is what you normally think of as a binary star, two separate stars. A semi-detached binary, though, would be where one star has already expanded and filled its Roche lobe, and then mass is starting to leak into the other star. If both stars fill the Roche lobes, we have what we call contact binaries, and these are two stars that are actually touching each other. And over contact binaries, and these are some of the ones I studied in graduate school, these are stars in which they're both filling its Roche lobe and they still try to expand, and they actually have gas in a cloud surrounding both of them, because you're overloading the entire. Okay, let's raise an interesting question. The star Algol, a Roche Algol, it's an eclipsing binary star. So every now and then the dim star gets in front of the bright star. And so it dims down, gets bright, and then sometimes when the dim star passes behind the bright star, it loses a little bit of light. But the problem is they figured out that this is a spectral type B main sequence star and a spectral type K off main sequence star. Well, that's okay. We expect that, but the problem is the low mass star is off the main sequence. We expect the high mass star to be the one that dies first. So what's happened here? Well, what we think actually has happened is that originally we had a high mass star and a low mass star, and the high mass star eventually left the main sequence. It filled its Roche lobe and started dumping stuff on the other star. So the high mass star lost mass and the low mass star gained mass. And that gave us the system that we have today, in which we have a high mass star, spectral type B, and it has more mass than the low mass star that's dying. And so the original star that died shed its outer layers, and so what's probably there is you have a very giant core with a very small outer layer that's spewing off into the other star. So this has substantially changed the character of this star. Well, this gives rise to the idea of the blue straggler. because now if you were to look at this star from a long way away, you would see a high mass blue star still in the main sequence. So that would explain the blue stragglers from the HR diagram of another possibility. What if you had a high mass star and a nearby low mass star? So as the high mass star started expanding, it would swallow the low mass star. Well, stars are actually very tough. So you might swallow a low mass star, and the other star would, for a while, maintain itself inside of the other star, orbiting inside of it. That's an interesting thing, because if you look at the star Betelgeuse, it's got a hot spot on it that seems to move around at a different speed than the rest of the star, suggesting quite possibly that's exactly what happened inside here, that we have a low mass star inside of a higher mass star that's died and is orbiting under the surface. And it might explain some of the weird stuff that's going on with Betelgeuse and why it doesn't behave the way that we kind of expect a really big star to behave as it dies. Should point out that stars that are more massive than about 4 solar masses actually go through a couple more stages to get to the point of making a red giant and a planetary nebula. As long as they get up to 8 solar masses, they will expel more stuff, so that they expel so much stuff that what's left is less than the Chandrasekhar limit. Most white dwarfs end up about 0.6 solar masses. So they'll lose an enormous amount of mass. Some of these things might still be a solar mass or so. Very rarely going to have more than a solar mass for a white dwarf. But they're going to lose so much mass, they're still going to be about half the mass of the sun as a white dwarf. Stars bigger than 4 solar masses are going to keep fusing a little bit. They're going to fuse some of the carbon and into neon, but they're eventually still going to run out. Stars bigger, however, than that are going to go another step. So stars up to 8 solar masses will undergo one more step. They'll fuse carbon into neon with a little bit of leftover helium, which can then participate in a little more fusion. But that's going to be the end state right there. Stars bigger than 8 solar masses, though, actually go through another step. So they'll actually fuse further. So even stars, they'll go through the step, but then what's going to happen is that core is going to fuse a little bit more. And so if the star's bigger than 8 solar masses, then it's going to go through another step, and it's going to fuse the neon into magnesium, and you have a little bit leftover oxygen. So what will happen is you'll end up with a magnesium oxygen core, and then neon shell fusing into the oxygen and magnesium, and then a carbon shell fusing in neon, a helium shell fusing into carbon, a hydrogen shell fusing into that, and the outer parts are going to still be hydrogen and helium. If the core gets bigger than 2 billion Kelvin, and stars bigger than 8 solar masses will do that, the oxygen in the middle will start fusing into silicon, and then again you have a leftover helium in there. And if it gets hotter than 3.5 billion Kelvin, and any star bigger than 8 solar masses is going to go through all these stages, the silicon fuses into nickel. The nickel is going to catch an electron and become a cobalt, which will catch an electron and become an iron. And that's it. Once you fuse to iron, it's not energy, you don't release any energy fusing anything else, and so the core is just going to be dead iron. So you have all these different stages of fusion going on in there. You have a hydrogen fusing into helium in a shell, fusing into carbon in a shell, fusing neon, which fuses into oxygen, fuses into silicon, and fuses into iron. The core is going to be iron. When the core reaches 1.4 masses, it's going to collapse. Again, just like with a white dwarf. Stars that are this big are going to be so hot on the interior, the outer part of the star is going to swell up all the way to Jupiter or more. And so that's a supergiant star. And so deep in the core of it is this tiny little shell that's fusing into something in surrounding another shell, fusing into something, fusing into another shell, and so forth. And then there's iron core in the middle. So these are the fusion reactions that go inside there. And so the iron core is the ultimate end to all that fusion. It doesn't fuse anymore and will keep fusing until you reach about 1.4 solar masses, and then it's going to collapse. And when it does, it's going to collapse violently and release so much energy that the entire star ends up exploding. That is going to be a supernova explosion.